So hello there and welcome to another exciting, how do I find this? I'm not sharing my screen yet, am I? No, okay. There it is. Okay, so let us start with chapter 1 on empirical and theoretical probability. So before we get into this PDF, does anyone think that they have a intuitive understanding of what probability is? Actually, I can do this before I start sharing. Anyone have an intuitive understanding of what probability is? That word, probability, what does it mean?
Like the chance of something happening?
Love it. So I did see a hand go up and then someone answered at the same time. So you can just answer. I expect like 6 people to talk the whole semester anyway. So if you know the answer to a question, just shout it out. And if it ever gets to the point that multiples are talking at the same time, then I will, change the policy. But yes, probability is essentially synonymous with the chance or likelihood that something occurs. And we have this, hopefully this intuitive idea or feeling that we know the likelihood of certain simple situations. And so that, for example, if I flip a coin and I say, what is the likelihood or probability that a heads shows when it lands? What would the answer to that question be? What is the probability that a flipped coin will come up heads?
50%.
So we have this idea that it's 50%. That's theoretical probability because we didn't actually do an experiment. We didn't actually run a simulation. We didn't do any actual activity. We just used our brains and came up with the answer based solely upon logic. But sometimes you can't do that. If I ask you, what's the likelihood that it's going to rain tomorrow? You can't just say it's 50% because either it rains or it doesn't. Just because there's 2 outcomes does not mean those 2 outcomes are equally likely outcomes. So how exactly would one perform? How would one come to the answer to that question? What the likelihood is that it rains tomorrow? How do meteorologists and the Weather Channel come to the conclusion?
Logging or keeping track, right? Logging.
Keeping track of what exactly?
Whatever it is that they want, like the weather on Tuesdays for once the whole summer, or if they want to keep winter weather on Mondays. I don't know.
Okay, I like some of what you're saying, but I don't like others of what you're saying, because you say Mondays and Tuesdays and the world does not know, the earth does not say, oh, it's Monday, so on Monday I'm going to do this, because it doesn't know this arbitrary division of time, correct? But I do like what you said about keeping track of various things. And someone said clouds and moisture and whatnot, which is also accurate. The true answer is, like a combination of the two, is that meteorologists have records of what has happened for every day of the last, let's say, 50 years when the weather was very similar to what it is tomorrow. In other words, half the time when it's this temperature with this cloud cover coming in and this, that, and whatever, I don't know weather stuff, but they look at the data and they say, in these situations, past experience has dictated that there's this chance of it raining, so we're going to use that number. That's what we call empirical probability, where you are using past data to predict future data. Theoretical is just common sense. Of course, we don't all have common sense. And sometimes you have to develop common sense and sophisticated mathematical techniques that allow us to compute what is common sense, versus empirical probability, which is based upon data. So the first chapter is on empirical and theoretical probability. Now, these PowerPoints, these PDF things, they come from the department as well. In past years, they have said, just go through the PowerPoint. Stop doing your own thing. This is all you're going to do and be happy. And I say, no, that's not how I teach. I like to elaborate. I like to go on tangents. I like to explain things. So it's going to be a combination of the two. We're going to basically be focusing on the PowerPoints, which is good because that way, if you miss class, it's not really that hard to follow because you have essentially what I'm going to do. But every now and again, I will add things that are not in here. Okay, so let's start. So empirical probability is based on gathering data often over the long run. So example, suppose that today's forecast says that there's an 80% chance of rain tomorrow in Northridge. This means that in the past, when the weather looked like it did today, it rains the next day 80% of the time, right? We're using past data to determine future likelihoods. So here's an example. You roll a die 100 times and get a 3 21 times. What is the empirical probability of rolling a 3? And what is the theoretical probability of rolling a 3? Let's do the theoretical probability first. What is the theoretical probability of rolling a 3?
1 out of 6, right?
1 out of 6, right? There's 6 equally likely outcomes. And of those 6 outcomes, there's only one of them that's a 3. So it's a 1 in 6 chance for getting a 3, correct? Seems relatively straightforward, I hope. Empirical probability means what is the likelihood of getting a 3 based upon past data? What is the data? Because I don't know if this die is fair. You're claiming it's fair, but I don't know if is it really fair? I don't know. So what does past data dictate is the likelihood of getting a 3 in my next roll?
21 out of 100.
So because 21 out of those 100 times I got a 3, that is the best I can say about the likelihood of getting a 3. The more times I do it, the more likely it is that this number is close to the true value, correct? If you roll a die once and you get a 3, are you going to claim that there's a 100% chance of getting a 3 because every single time you roll the die, you got a 3? That's nonsense, hopefully, right? The sample size, the number of trials that you run has to be large enough to really make the prediction somewhat valid. Does that make sense? Yes, no, maybe so?
Yes.
How do I, okay, so
Yeah.
I have to delete the eraser. All right, so it's pretty easy so far, right? Right, we're 1 page in, everything's great. All right, so here is a situation, and I love this particular example. In the past on quizzes and homeworks, you see very similar things. You take a nickel and you bend it. So even if it was fair, we really don't know whether or not the likelihood of landing heads or tails would remain 50-50. Agreed? Right? I don't know the physics of bent nickels. But what we do is we take this nickel, we bend it, and then we flip it 25 times. If you look at the graph, you will see 25 dots, I hope. Otherwise, this is really going to be awkward. But I see 25 dots. Each dot represents a flip. The vertical scale is not how many heads you've gotten, but rather it's the proportion of heads. So the first flip, what is the proportion of heads that I've received after the first flip? What proportion of heads did I get on all of my one flip so far, how many of them, what percentage of them have been heads?
100.
100, which means was the first flip a head or a tail?
Ahead.
The first flip must have been a heads so that the percentage of flips were heads after I'm done with the first one, correct? Yes, no, maybe so. If this is not making sense, you have to say something because I don't see many faces when I'm looking at, when I'm sharing my own screen. So I don't even know who's nodding and who's not nodding. After the second flip, what is the percentage of heads that I've received in total of my two flips? Okay, that's an interesting noise.
Is it still 100?
It's still 100%. So what was the second flip? Was it a heads or a tails?
Heads.
It's still heads because my percentage of heads is still 100%. Now, what is the percentage of heads after the third flip?
66%.
66% approximately, which means the third flip must have been a what?
Tails.
Must have been a tails. And essentially, what you see, as I move down this graph, sometimes it goes down, sometimes it goes up. What is the general pattern that I can just look at the graph and not even worry about the numerical values to determine whether a flip was heads or tails? What's the relationship between the shape of the graph and recognizing whether a specific flip was heads or tails?
If the graph goes up, you're getting a heads. If it goes down, it's a tails.
Awesome, right? Every time the graph goes up, the percentage of heads increases, which means I must have received a heads in the next one. And every time the graph goes down, the percentage of heads goes down, which means I must have gotten a tail. So what was the last flip then?
A heads.
The last flip must have been a heads. In fact, let's go one step further. How many, I don't even know, I don't remember what the next page reads, so this might even be on the next page somewhere, but how many heads did I get altogether?
Is it just 2?
Well, every time the graph goes up,
Oh,
I know that I got a head, right?
okay.
Right? So I started with 2, definitely, heads and heads. The next one was certainly a tails. But what was my fourth flip?
It was a heads.
It was a head, so it's got to be more than 2.
Okay. Okay.
So how many heads did I get altogether? But don't worry, wrong answers are still better than just utter silence.
If I counted correctly, you got 15.
Okay, well, I
Going 17.
think I counted correctly, but I didn't. How do I see
Is
it?
it 19?
Well, 19. Okay, I didn't.
Maybe I'm wrong.
I got 16.
I got 16 as well.
I got 6. I got 16.
Oh yeah, my bad. Yeah, I'm sorry.
I got 16 also. You had the first 2.
Yeah, I missed
Down.
out. My bad. Yeah.
Oh, more chatting. Hold on. I got 16 now. Excellent. So 1, 2 down, 3, 4 down, 5, 6 down, 7, 8, 9, 10, 11 down, 12, 13 down, 14 down, 15, 16. I got 16 heads. So after I'm done with the 25 flips, if I had to make a guess as to the likelihood of the next flip being heads, what would be the best guess that I can possibly make for the next flip being heads after I flipped it 25 times with this particular collection of outcomes? What would be your guess for the probability of a head on flip 26? I can't write like this, but it's fun anyways. What is the probability of a flip on heads 26? I got a 16 out of 25, which I completely agree with. Because of the 25 flips, 16 of them were heads. So it seems that the likelihood of getting a heads using all of the data that I have at my disposal would be 16 over 25. Does that make sense?
Yes.
Okay. So let's see if that question was asked on the next page. So based just on the 25 flips, what is the empirical estimate of the probability this nickel will land heads? Yes, so there it is. The answer there was 16 over 25.
So would you like us to leave it in fraction and not say like 65%?
Well, 16 over 25 would be 64%. But that's okay. I love fractions. I prefer them to decimals and percent symbols, but I will accept either one.
Okay, cool.
Okay, or either one of the three, I guess. So I might leave it one way, one problem, and leave it a different way the next problem, and a different way the next problem. It's all numerically equivalent. Okay. So now, if you go back to that example, in the beginning, we kind of see that the percentages is kind of adjusting itself. It's all over the place, right? It's high, it's low, it goes up, 14%, back down, up. It's kind of adjusting, correct? But what do you see in the long run? Okay, this is a different problem because we see it dropped immediately on the second flip. So this is not the same data. But here we have a situation where a coin was flipped 30 times and the proportion of heads is listed. What do you see in terms of the, oh, by the way, one last thing, going back here again. 16 over 25 was 64%, and notice that that's exactly where we end up. So the vertical scale here is just giving us that value of the likelihood that the next one is going to be a heads. Do you all see that? Hopefully some of you. So notice that in the beginning, there's a lot of fluctuation in terms of what that likelihood is going to be. But what happens as the number of trials gets larger and larger and larger?
It gets closer to 50%.
Well, not necessarily 50, although it did in this case.
Mhm.
Okay, I don't know, for example, if the coin is fair or not. But what I do know is that it kind of stabilizes around some value. Lots of fluctuation in the beginning, but as the sample size increases, it kind of seems to stabilize around the specific value. This is the very important law of large numbers. In random situations, a random situation is one where the outcome is unknown in advance. As the number of trials increases, the proportion of successes approaches a specific value, which we call the probability. And we should say the empirical probability because it's coming from data. If it's a fair coin, we do expect it to stabilize at around 50%. If it was a weighted coin, it could be anywhere from 80, it could be anything. Right, does that make sense? Any questions? Okay, good talk. All right, so what is the probability of heads for a coin flip? It seems to be 50%. What is the empirical estimate here? Well, if I use all of my data, which is all 30 flips, it certainly seems to be 50%. Had I stopped at 10 flips and I said, what is my empirical estimate for the likelihood of getting a heads? What would the answer be?
64.
Sorry, if you stop at 10 flips,
Would it be 40%?
it would be at 40%, right? If you stop at 10 flips right here, the best you can say, right? At that point, we don't know any of that information past 10, right? That's all we have to go on, correct? So it would be 40%, 0.4. But since I have all this extra information, I might as well use it. Why ignore those additional 20 flips? And my final answer would be 30%. Do the results illustrate the law of large numbers? Does this graph seem to illustrate the law of large numbers?
Yeah.
Yeah, right? As the number of trials, and let's see, someone chatted what they say, hopefully yes. Okay, there you go, yes. right? As the number of trials increases, we get stabilization. That's essentially the law of large numbers. Okay, so let's take a look at this example. People often wonder how polls can be accurate when they were not asked for their own opinion, right? You ever see that on the news? So this many people are going to vote for so-and-so. And you're like, well, they didn't ask me. So how do they know? So people often wonder how polls can be accurate when they weren't asked for their own opinion. A Gallup poll asked a random sample of Californians whether they believe that teachers in the city or area where they live are well respected. Assume that if every Californian had been asked, 75% would have said yes, which, by the way, is what the Gallup poll concluded. So this graph below indicates what might have happened as the sample size got larger and larger. What is the difference between the beginning of this graph and the end of this graph?
It plateaus like at the end.
It does plateau, but that's not really the point that I'm trying to illustrate. The end is more stable, right? In the beginning, we have lots of fluctuation, right? It goes up, down, up, down, up, down. It's fluctuating all over the place, right? Fluctuating less and less. But at the end, we see that it's essentially fairly constant. Do you agree?
Yeah.
The law of large numbers is not about plateauing, it's about fluctuation. We expect lots of fluctuation in the beginning, not always, we could get lucky, but certainly we want stabilization at the end. Now, if I had stopped after asking 100 people, then what would your estimate have been of the number of Californians who said yes? Approximately, can't get perfect. It's hard to see the scale. But if we had stopped at 100, what would your estimate have been of the proportion of Californians who said, yes, we respect teachers?
Would it be around 80%?
It certainly seems to be somewhere in the vicinity of 80%. So let's see, someone chatted. Yeah, about 80%. If I stop after 500, what is it now?
Like 71, almost 70, around there. Like,
Yeah, well, 70 is this. 70 is here.
oh, I'm sorry. So yeah, I saw. So like 75, 76, around
I think higher. I think maybe 77.
there.
Maybe.
76, yeah.
Yeah, a little higher than 75%.
Maybe you will be looking at like 78.
Maybe even 70. It's hard to see, right?
Yeah.
It's hard to see, but somewhere in that vicinity. I mean, the blue line is 75%, so it's certainly above that.
Yeah.
But yeah, 77, something like that percent. So you see it changes, but it certainly has stabilization the further we go down the line. And that's really the point. And if I had stopped after 600, it said Gallup actually used a sample size of 600. Does that seem adequate for getting a conclusive, correct value for the true value of all Californians?
No.
Why not? We're only 1% off the true value.
Oh yeah, that's true.
I mean, you can't expect any sample to be perfect, right?
Let me see if I have 100 people.
Right?
Not
100
usually.
people is pretty far off. 80%. I mean, it's only 4%. It's true. But it certainly seems that by 600, you have essentially the same value that you're going to have straight up to the end.
Yeah, the 500 and 600 people. Yeah. it does.
Yeah. So this is how polls work. They obviously can't ask everyone. We don't have the time and we don't have the resources to ask everyone what their opinion is. So we're going to take a sample size large enough that we feel that the results of the sample would be representative of the entire population. This graph certainly seems to indicate that if we stopped at 600, we're certainly in the right ballpark. Correct? And as we go, yeah, go ahead.
The sample size of 600 representing almost 39 million, that's a decent sample size in this case.
Yeah.
I'm just curious.
Yeah. And I'll give you an example of this. People are a little surprised about that, but let me ask you a question. Have you ever cooked soup?
Yes.
Okay. So if you're cooking soup for yourself and you want to test if the soup is ready, what do? What's one thing you could do?
Taste it? I don't know.
Taste it, right? You take your spoon you dip your spoon in there and you, okay, I'm good to go, right? Now, imagine you make a pot for like you're catering an events. So you have this huge pot of soup. Are you going to take a bigger sample of soup to see if it tastes okay? Or will the small same size spoon work even though the pot itself is so big?
Okay, that makes sense, yeah.
Okay, so if the sample is large enough, and here 600 seems large enough, it's surprising that that would work even for true populations in the millions. Okay, and we're going to see as the semester progresses, we're going to see, we're going to get into the numerical aspects a little bit, not too much. But and in a more advanced course, you would certainly get into the numbers and you would see that yes, 600 is more than large enough. Okay, all right.
Perfect, thank you.
So, all right, so let's pretend to do a group activity because we're not in groups. So it says your 6th grade class begins to flip a fair coin. And the first 6 flips are all tails as shown in the graph below, right? So we have 6 dots. The first, the second, the third, the fourth, the fifth, the sixth are all tails. So 2 of your students disagree on what will happen next. Ava says the next flip is more likely to be heads than tails because by the law of large numbers, the number of heads and tails has to even out. We'll assume it's fair. Pablo says the next flip is equally likely to be heads or tails because the coin cannot remember what happened before. Of those 2, which one is right? Is Ava right or is Pablo right? Or are both of them right? Or are both of them wrong? So if you have to read that again, make sure you understand what's going on. And then share with the class your opinion.
I agree with Pablo
Okay.
because I think he's right that the coin isn't looking at empirical data as it goes. Unless like it does have like a deformity that makes it land one way specifically.
Well, let's assume it's fair. We'll assume
Right,
it's
okay,
fair.
yeah.
And in fact, that's even part of the question, right? They flip a fair coin.
Oh, gotcha.
So we don't have to assume it's fair. It is fair. So you agree with Pablo. So you are ignoring the law of large numbers. You're just saying, Ava, you don't know what you're talking about.
Well, because they haven't done like a lot of numbers.
That's true. They haven't. Does that mean the law of large numbers doesn't start to exert itself until the number gets large? Or will the law of large numbers try to ensure that as the number gets bigger, it goes in a certain direction?
Right.
Okay, so this is a very interesting aspect of probability that is on the surface very almost paradoxical. It is impossible to determine what's going to occur on any given flip. Because as Pablo says, the coin has no memory. It doesn't know what's happened before. So the flip 50-50. But yet the law of large numbers says, as the number of flips gets larger and larger, the proportion of successes, in this case heads, should converge to the true value of 0.5. So the law of large numbers says, if the number of flips is large, I can tell you what's going to happen. Whereas the rules of probability say, for any given flip, I can't tell you anything about what's going to happen. So we cannot predict anything for any given flip, but we can predict in the long run what's going to happen, which I think is very strange, even as someone who studied probability for years. That on any given flip, I can't tell you anything, but if you put all the flips together, I'll tell you exactly what happened. Hopefully you should be like, what? But I just see a lot of blank faces and stuff. So I'm just going to keep going because you guys just don't appreciate. Sorry. Breathe, breathe, breathe. Okay. So the answer was Pablo was right. The coin has no memory. We have no idea what's going to come next. However, in the long run, I can predict that the proportion will eventually reach 50%, but I have no idea what's going to happen. on the next coin. How might you convince the class of this? Well, I guess one way would be everyone flips the coin and we see that about half of them are going to be heads and about half of them are going to be tails. That's what I expect to happen. Anything can happen on any given flip. Does that seem reasonable?
Yes.
Okay, thank you for acknowledging my existence and
Just a quick question.
yes.
So what Ava is saying is that eventually, like the larger amount of flips that there are, it's gonna reach the 50
Yeah,
probability.
it should be somewhere around 0.5 as the number of flips goes up. Now, I don't know if that's going to happen by 40 or by 400 or by 4,000. I don't know how long it's going to take, but I can say that by the time the number of flips gets to about, a certain number, I should be in the vicinity of 0.5.
Oh, okay.
Okay, law of large numbers, I mean, that's what large means, right? It only applies for a large sample size.
Okay.
How large is large? Well, sometimes you'll start around 0.5. Here, I mean, if you flip the coin 6 times, do you expect to get 6 tails in a row? No, I mean, in fact, if it happens, I'd be a little surprised. Not enough to say this coin ain't fair. What are you talking about, Willis? But I'd still be a little bit surprised, right? Yes?
Yes.
Okay. All right. So we're not going to do this because, well, I don't want to flip anything 1,000 times. But how about this? Let's make up numbers. Let's make up reasonable numbers. I know that I have 6 tails in the first 6 flips. After 10 flips, what is a reasonable expectation for how many heads I have in total? Not, huh?
Wouldn't it be 6?
So you're saying if my first 6 flips are tails, then after 4 more flips, I will have a total of 6 heads?
No, I mean, sorry.
I would think about
4 heads.
4 or 3.
Well, one second. If you say 4 heads, if you don't write this down, but if you say 4 heads, then you are predicting that all of the next 4 are going to be heads. Because I began with 6 tails, right?
Yeah.
Yes. So if you say the number of heads after 4 more flips is 4, means that you are predicting 4 heads in a row. It's certainly possible to get 4 heads in a row, but is that what you expect to occur?
No, not really.
What do you expect to occur? How many heads do you expect to occur in the next 4 flips?
Yeah, let's do around 2.
Around 2, I would expect, right? Which means in total, after 10 flips, I would expect somewhere in the vicinity of 2 heads. Would you agree?
Yeah.
For a proportion of heads after those 10 flips of how much?
2 wouldn't it be 2 out of 10?
Yeah, 2 out of 10, which is 20%. Do we agree?
Yeah.
Now, after 10 more flips, what's a reasonable expectation for the number of heads that I would have in total after those 20 flips?
Around 10?
So you're saying I would get 8 flips in the next 10 flips. Is that a reasonable expectation?
No.
It's not impossible, but is it reasonable? What's a reasonable amount of flips of head? Huh?
Do 4.
4 total or 4 more?
4 more.
Okay, 4 more is reasonable because in the next 10 flips, I would expect somewhere around 5. So 4 seems reasonable for a total of 6. Do we agree?
Yeah.
Yes. Okay, and in that case, what would the total proportion of heads be now if I had 6 out of 20?
30%?
I would now have 30%. Yes?
Yeah.
Yeah.
Okay, so now I'm going to do 80 more flips. After 80 more flips, what is a reasonable total number of heads to have? I have 6 already. I do 80 more flips. What's something that's going to be presumably in the vicinity of the true value?
40?
Okay, 40 sounds reasonable. I mean, if I have exactly 40 heads, 40 tails, that would be 46. So anywhere that's in the ballpark of 46, 40 is pretty okay. For what percentage of heads now?
40.
40%. So look what's happening. Just by my normal expectations of how many heads I expect, what's happening to the proportion?
It's getting closer to the 50%.
It's just naturally getting closer to the 50%. Without me even doing anything special, just saying, this is a reasonable assumption. It's naturally getting closer to the value that I would expect it to have anyway. And if I did 900 more flips, what's a reasonable number of heads? The 40 that I already have, plus what I get in 900 more flips, what's a reasonable number?
450.
Okay, 450, which is now 45%. So these are all reasonable values. Again, I don't know about you, but I do not want to actually do an experiment flipping a coin 1,000 times. Unless one of you wants to. Anyone want to spend their Saturday doing this? This would be a hoot for nobody. Luckily, in the next chapter, we are going to learn about simulations, which are ways of representing doing an experiment like this without actually having to do the experiment. But what we certainly see is that these numbers are naturally getting closer to the expected value in the long run, which is 50%. This is the law of large numbers. Does that make sense?
Yeah.
Okay. If not, at any time, just say the magic word. I don't know what the magic word is. Now, do the number of heads and tails even out?
Eventually we'll get to the 50, like close to it.
Close to it. Close to it. Which means not necessarily.
Not necessarily, but close to it.
Right. I can't spell like this. It'll take me forever, but not necessarily. But does the proportion of heads tend to get closer to
There you
one
go.
half?
Yeah.
And the answer is yes, right? So there's no need by the law of large numbers for things to balance out. You don't say, oh, you got 6 tails. Let me give you 6 heads to balance it. There's no balancing when it comes to the law of large numbers. There's just the natural approach to the true value by expectations. Okay? So that's the illustration that I'm trying to make here. Hopefully it came across. And by the way, just so you know, here's what actually happened on the next 94 flips. So after 10 flips, how many heads were there after 10 flips based upon this this data?
It'd be 3.
3 heads, right? Because we went up and then up and then up. 3 ups in the first 10, correct? So there were 3 heads in the first 10. How many heads were there in the first 20?
4.
In total?
No, there was 5, wasn't there?
Let's take a look. 1,
Right?
down, 2, 3, down, 4, 5, down.
Oh, I'm
6,
sorry. 6.
down. I get 6 heads, no?
Yeah.
Which again is a little surprising. Not what I would expect. How about after the first 100 flips? How many heads were there now? Now, I don't want to do it by actually counting how many ups there were. That worked in the short run, but in the long run, we want to have an easier way of computing it. So how do we compute the number of heads in the long run after 100 flips?
We can use the decimal it lands on and then multiply it by 100.
Yes. The percentage of heads was what? What decimal is this? Point what?
It's under 0.5. I can't tell exactly what it is.
Yeah. So here's 0.4, 0.42, oh wait, this is 0.4, 0.4, 0.425, 0.45, 0.475. I would probably say, I don't know, 0.47. Does it look like it's about 70% of the way through? Yeah, okay, so it
Yeah,
looks
'cause
like,
the other one will probably be
So
like the one next
47.
to it.
So
Yeah.
47.
I would say 47 heads. So notice how it naturally is getting closer to 50% on its own. We all agree?
Yes.
Any questions on this so far? Does the graph illustrate the law of large numbers?
Yes.
Yeah.
Yeah, we got lots of fluctuation in the beginning, and it certainly seems to stabilize, or at least it's on the way to stabilization. It still is shooting upwards, right? Doesn't quite yet reach stabilization, but there's a lot less fluctuation here than there was in the beginning. Okay, so that's the first half of today. Now let's go to the second half. That was all about empirical probability. Okay, that's all using data to calculate likelihoods based upon past information. Now we're going to look at theoretical probability. Now, when it comes to theoretical probability, there's two scenarios. There's something like flipping a die, flipping a coin, picking a card from a deck. And these all have the mathematically important aspect of having equally likely outcomes. Okay, when it comes to math, actually solving problems, situations with equally likely outcomes are a lot simpler than situations where they're not equally likely. If I say, oh yes, it's so nice, you're having a baby, do you know if it's a boy or girl? Oh, we're waiting, we don't know yet. And I say, well, what's the likelihood of it being a boy? Not getting into the gender fluid aspects, but just purely biological. What's the probability of being a boy? Or a girl? Anyone?
50-50.
50%, right? It's half and half, correct? Right, 50-50.
But what about like intersex people?
Again,
born-
so not getting into the gender fluid type situation. So
But like intersex is like they have different genitals, both sexes.
so again, the likelihood of something like that occurring is so close to zero that we're essentially going to ignore it. And again,
Gotcha.
remember also that your intended audience are usually elementary school children who would probably find the topic like that immature in the first place, or they'd be immature about it. And you probably won't want to complicate things. I mean, you're right. I mean, it is something that would need to be considered if you were doing like a study at a research level. But when you're trying to keep things straightforward and simple, we'll pretend that it's not to have situations like that. Is that fair?
Yes, that makes sense. Thank you.
Okay. So I kind of lost my train of thought there. So, oh yeah, so I was saying, we know that the likelihood of having a boy or a girl is 50-50. But if I said, oh my God, you have 4 children, they go, yeah, I have 4 children. And I said, what's the likelihood that one of those children is a boy versus girls? In other words, not 2 boys, 2 girls, or 3 boys, 1 girl, but 1 boy and 3 girls. It's no longer an equally likely outcome scenario, because the likelihood of having 1 boy is different than the likelihood of having 2 boys or 3 boys or 4 boys or no boys. They have different values, which we will calculate in the days and weeks to come. Okay, so it's very important to always recognize when we're dealing with an equally likely outcome scenario versus a non-equally likely outcome scenario. But either way, there are certain aspects of probability which are always satisfied no matter what. This first one is one of the big ones. Any probability must be between 0 and 1. 0 means it cannot occur. 1 means it will definitely occur. And a number between 0 and 1, that's when it might occur. Do we all understand why it can't be less than 0 and greater than 1? Okay, if it's definitely going to occur, then how do you get more likely than that? And if it can't occur, which is 0, how do you get less likely than that? Agree? Yes? No? Acknowledge I exist,
Yes.
please. Thank you. Even just saying yes, just acknowledge.
Yeah,
I
makes
exist.
sense.
Okay. Now, an event is a collection of outcomes from the random situation. Suppose I roll a die, a regular good old-fashioned 6-sided die. How many outcomes are there legitimately? We're not going to count landing on its edge or spontaneously hovering in the air and never coming down, right? Just standard. How many outcomes are there if I roll a die? Six. There's 6 outcomes, right? But when it comes to an event, there's many different events. I can say as an event, rolling an even number, right? This could be an event, rolling an even number. If I'm talking about the event rolling an even number, which outcomes would apply to rolling an even number? What? Sorry.
3 out of 6.
Well, not the likelihood. I'm just asking, what is the event rolling an even number? What would comprise rolling an even number? If you had to list the outcomes for even, what would they be?
2, 4, 6.
2, 4, 6. It is a collection of outcomes. An event is a collection of outcomes. In this case, it's the collection of 2, 4, and 6. Okay, if I said the outcomes greater than 3, would that be a legitimate event for rolling a die? Outcomes greater than 3, what would that event be?
4, 5, 6.
4, 5, 6. So any event is just a collection of outcomes. Okay. If it cannot happen, its probability is 0. What is the probability if I roll a die of getting a 7.2? 0. Can't happen. What is the probability of rolling a number less than 12?
100%.
Definitely going to happen. 100%. Perfectly legitimate events. Correct?
Yeah.
Skipping this one for a second, we'll get back to it. The likelihood that event A does not occur, the probability of not A, is 1 minus the probability of A. Okay, let's think about why that should be true. Maybe there's some examples here. Yeah, there'll be an example in a second. So we'll illustrate that in a second. And then finally, the big formula here. If the outcomes are equally likely, and there are n of them, each outcome has probability 1 over n. And therefore, if I want the probability of the events, I add up the number of outcomes in the event and divide by n. If you look at the example that we just did with the even, how many ways are there of getting an even number? When you roll a die, how many ways are there of getting an even number?
3.
3 of them.
3. How many events are there, and how many outcomes are there in total?
6.
And that's why the likelihood, the probability of getting an even number would be 3 out of 6. Because there's 3 ways of getting it. There's 6 outcomes altogether, 3 out of 6, 1 out of 2, 50%. Does that make sense?
Yes.
Of course, this only holds if they're equally likely. Do not try to apply this formula otherwise. So, example. Each student in Math 211 writes his or her name on a slip of paper. We draw one slip at random. Let event F be getting the name of a female. What is the number of possible outcomes n? Well, to answer this question, we would need to know how many people are in the class.
37.
37. Where's that? Is that number of people in the room right now in the chat room?
It's 36, not counting you,
You,
Professor.
yeah.
Oh, thanks. Don't count me. I appreciate that. I've always known I was. Okay. So there's
Not,
30.
not to be offensive, not to be offensive.
No, I'm very offensive. Okay, so 36 possible outcomes if we're not including me. Although Michael, did Michael ever show up? You there, Michael? Okay, so he's not here. So there's actually 37 people in the class, but we'll just do 36 of the people in this room. Now we want the probability of getting a female. Now, I don't know necessarily how many people in this class are female or identify as female. Looking at the roster, it does seem that there's more males than females. So let's actually do this. If you are a male, type in the chat something, and then I will subtract that from 36, and we will assume everyone else is female. So Alexander typed something, so that certainly qualifies. 2, going once, going twice. Okay, so that 3, and I think there was Junyin. Are you here still, or did you leave the class? Oh, Jason won. Did you change your name to Jason?
Yeah.
Okay. All right. So it looks like there are 3. So that means, what is the probability of me drawing the slip of a female? What number would go on top?
33.
33. There's 33 females, unless someone else chatted. Oh, no, she's answering. Okay, 33 females, and therefore, the probability of me picking the name of a female, 33 over 36. Therefore, what is the probability of not picking a female?
3 out of 36.
And how do we get that? 1 minus the probability of picking a female. And if we get a common denominator, 1 is 36 over 36. So 36 over 36 minus 33 over 36 is in fact 3 over 36. If it has to be one or the other, then they have to add to 1, because you got to get something. Right? Are the events F and not F equally likely in this scenario?
Wait.
That's no.
No, we're not.
Right.
They're not even close, right? The likelihood of getting F is 33 out of 36. The likelihood of getting not F is 3 out of 36, right? These are not even close to being the same. I guess there might be classes out there that have, like 18, and their answer would be yes. Right?
Yeah.
Okay. Next concept is that of a sample space. Every experiment has a sample space. The sample space is the collection of all possible outcomes. When you roll a die, what are the collection of all possible outcomes? Not how many outcomes are there, but what are the actual outcomes when you roll a die?
1, 2, 3, 4, 5, 6.
So that would be the sample space. The sample space would be the collection 1, 2, 3, 4, 5, 6. If you flip a coin, one coin, what is the sample space?
Heads or tails?
Heads or tails. Usually we can denote it like we do here, H or T, but yes, heads or tails. Not 2. You don't say the sample space is 2. No, it's not. There are 2 things in the sample space. That's true, but the sample space is heads, tails. If you pick a card from a regular deck of cards, no jokers or any nonsense like that, then how many elements are there in the sample space?
You mean like spades, diamonds, hearts, clubs?
Sure, but so you're saying there's 4 elements in the sample space?
Yeah. Or do you mean numbers too?
Well, what are the outcomes? If you pick a card, would a 2 of clubs and a 7 of clubs be considered the same outcome?
No. So
No.
then it would also be the numbers.
So how many outcomes are there in that sample space? When I was a kid, we all played cards because we didn't have computers and whatnot to waste our time. So we played cards to waste our time.
52.
So there's 52 cards in a deck, right? So the number of elements in the sample space will be 52. Ace through king of the 4 different suits. I have actually met people, I'm not claiming anyone here falls in this category, but I actually have met people who had no idea what a deck of cards was. It's hard teaching a probability course without that level of the example, but I have met people like that. They are weirder than I am. Okay, so here's an example. You ask your 5th graders to write a sample space with equally likely outcomes for the situation of flipping a penny twice. Here are 5 responses. 2 heads, 1 head and 1 tails, 2 tails, a head then tail, a head then head, a tail then tail, a tail then head, HH, HT, THTT, 2 of the same or 1 of each, and 0 heads, 1 heads, or 2 heads. Which of these are legitimate sample spaces? And of those, which of them are sample spaces with equally likely outcomes? So which of these are legitimate sample spaces? I'm sorry, a little louder, hard for me to hear.
I think they all are, right? They all could be.
2 and 3.
Well, let's take a look. Remember, a sample space is the collection of all possible outcomes, correct? If you're after how many heads, if that's the goal, then number 1 is a perfectly allowable sample space. Because what are the possible number of heads? 2, 1, or none, right? If we need more information and we want to know the exact outcomes in order, like head then tail, head then head, tail then tail, tail then head, then that's a perfectly allowable sample space. In fact, these 2 are really the same, right? The third one is merely a shorthand notation for the second one, correct? Yes? No?
Yes.
And
Yes.
which other 2 are really the same?
2 of the same, 1 of each is the same as saying 2 heads, 2 tails, 1 head, 1 tail.
Is it? Here there's 2 outcomes, 2 of the same, 1 of each. Here there's 3 outcomes.
Oh, I thought it meant like 2 of the heads and then 2 tails.
Right, but when they say 2 of the same, 1 of each,
Oh, that's the last ones.
yes, but 1 second. When they say
Okay.
when they say 2 of the same or 1 of each, as these are my possible outcomes, they're lumping together 2 heads and 2 tails into the same.
Oh,
Do you see that?
yes.
Okay, so the other one, what do you say? I don't have names yet to voices, but which other 2 are the same?
Is it 2 of the same? So it'd be 2 heads and then 1 of each, 1 head. Those are the 2 last ones?
But again, this is 2 outcomes. This is 3 outcomes,
Oh,
right? But these 2 are the same. 2 heads, 2 heads, 2 tails, the same as no heads, and 1 head and 1 tail is the same as 1 head. Right? It's just different ways
oh
of saying
wow.
something,
How the kid spelled it. Okay.
right? So really all 5 are sample spaces depending on what you're after. If the question is, did I get the same or not? Then that's all 4 cares about. If it's how many heads did I get, then that's what 1 and 5 care about. And if it's what did I get on each coin, then that's what 2 and 3 cares about. So depending on what you're after, technically all 5 are valid sample spaces, but they're not all valid sample spaces with equally likely outcomes. But either way, it is 3:15, and I don't like going over because people have places to be and things to do. So we will stop here for today at 3:15. We didn't quite finish page 10, and therefore we didn't finish the first chapter. So there's no official homework due. However, by this point, we have done most of the chapter, so I would get started on it. Again, I'm not collecting the homework. You do what you want for your own benefits. But I take quizzes and tests from the homework. So the more you do, the better it'll be for you. So there's 9 questions. Since we didn't finish chapter 1, I'm not officially assigning this until next time, but we will certainly finish it on Thursday. So therefore, the first homework will be due next Thursday. You always have a full week from when I assign it. So the first homework will be due next Thursday, but I will start answering the questions now. Someone asked, raised their hands. I'm gonna stop sharing for a second, but who raised their hand? What's going on here? Yes, go ahead.
For the homework, where is it gonna be on Canvas so we can do it?
The homework is on the, as part of the PDF. The homework's at the end of the chapters.
Okay, thank you.
Right, so in the PDF that we just went through, the homework's at the last few pages of the homework pages.
Are they gonna be on Canvas though?
You mean the solutions, or the solution's gonna be on Canvas?
Okay,
I will put the solutions up, but not until after the due dates, because I want you to work on them yourself.
When's our first quiz, Professor?
Oh, I don't know. Probably not till we finish at least 2 chapters. Actually, I don't know, maybe we'll finish after the first chapter. Why don't we have it next Thursday? How's that? First quiz, first chapter. What do you think? Get it out of the way. You know, that way you can all drop if you fail, and I can get paid for teaching. Anyway. What do you think? And by the way, just so you know, I don't want to waste class time for quizzes. So the quizzes will be on your own, like they'll be like homework. I'll assign a quiz and I'll say submit it within 2 hours or whatever, something like that. So that way you do it on your own. You don't do it during class. Okay, because otherwise it just takes too much time. All right, any questions? I'm gonna stop sharing now or stop recording.
Like, is there a time limit?
Well, yeah, I said like within 2 hours, so that yeah,
Okay.
seems to imply, yeah. But sometimes I might give you like the weekend, hey, you know, get it to me by Tuesday or something like that, just because, you know, I'm lazy and stuff. Okay. Sounds good, thank you, with an exclamation points. I like lots of exclamation points. Okay, now you all get to leave and I get to see who sticks around and I get to take off attendance. So I will see you all on Thursday. Peace.
Thank you.
Thank you, Professor.
Thank you.
Yes,
Thank you.
sure.
Thank you.
No problem. Huh? Okay. And then where were 2?
Professor, I have a question.
Yes.
I'm in your upcoming class right now at 4. We meet on Zoom, right?
All classes are on Zoom and only on Zoom.
Okay. Sounds good. All right, I'll see you in a little bit.
Wait a second. Wait, don't go anywhere yet. I don't see you. Oh, are you in my next class?
Yeah, that's what I said.
Oh, okay, no problem. Okay, catch you later.
Okay.
Okay, bye.
Hi, Professor. I have questions.
Okay.
So the home